So I guess we can jump on in. So I guess maybe the first thing I'll mention is that so wrote some kind of wrote some paper. I guess this was sometime last year, and so you can find that one here. It has actually there's a lot of stuff there. Basically, what I'm going to talk about here is kind of a summary of some of those main things, plus maybe a few other little tidbits as I go. So focus here is on some notion of false confidence, how this is related to, here I'll refer to them as some kind of non-additive beliefs, but in some sense this is kind of I guess bigger picture is kind of related to some imprecise probabilities and kind of how does this fit into the notions of statistical inference. So if there's questions or anything as we go, I mean, it's fine to jump in and interrupt. I guess I'm not a Zoom guru, so I'm not sure. I think if you post a comment or like a chat thing or something, maybe I get some message, but feel free to just unmute and yell at me if you like. Okay, so of course, statistics has a lot of stuff going on. It's been now a relatively old kind of field, and been some substantial things have happened in last 50 plus years. I guess one thing that is sort of interesting is that we're still kind of operating in this in some kind of frameworks that were sort of set forth actually a long time ago. And so there's a number of things that are still some kind of questions that have yet to be unanswered that are kind of related to some kind of more fundamental things about statistical inference. And in particular, like how does probability, what kind of role does probability play in statistical inference? And so there's sort of two standard or two dominant schools of thought in statistics. This is talking about like frequentist and Bayesian, and they use probabilities in actually very different ways. And so, most of the discussions about these different kind of things is about which one is right in some sense. There's all sorts of senses in which you would talk about something being right. But this, in some sense hasn't really helped because, frequentist and Bayesian things have been debating about things for maybe since definitely in like the, early part of the 1900s, and nothing's really changed. There's, in some sense, we've just decided to stop fighting, not really that we've resolved anything. So what I want to do here is to focus on what I think is important for science and also for engineering, and like how does the statistics sort of fit into that. There's some notion of reliability, and so here I just use that word because that's kind of a more maybe a more standard type of term. Later, I'll have a more precise definition with a different name. This is related to that notion of validity that was mentioned in title. Okay, so let's set up some kind of notation and terminology here. So what I want to say here is, so the statistical problem will be a generic one, at least here to start. We'll focus on some specific things later as we move along. So what I focus on here is data is some y. So this is something that we're able to observe. So how I've written it here makes it look like data is just like one number, but of course this y could be anything. It could be a vector of some IID things. It could be all sorts of complicated objects, so that I don't need to say anything about what specifically y looks like here. Examples will be relatively simple ones, but this really no loss of generality, just label this guy as y. And then along with the data that we can observe, I want to have a statistical model. Okay? And so the statistical model is just a class of probability distributions. These are distributions for y that depend on some parameter theta. So like examples, of course, are like things like a normal distribution where the parameter would be the mean and the variance. And so if we're dealing with such a problem, then maybe the mean and variance are both unknown. And so then we'd like to do some kind of things like to estimate those parameters or to answer certain kind of questions. And so once this model has been specified, then all of the sort of relevant scientific or engineering related questions would correspond to various hypotheses about this unknown parameter. Okay, so what's the goal here is to be able to quantify the uncertainty about that unknown parameter given the data that we can observe. And so there's various ways that you can think about doing this. What I thought was try to set kind of a very general type of framework is to say, well, what I want to do is I want to be able to return some kind of measure, some kind of quantification of my uncertainty about various hypotheses. And so a way to imagine doing that is to construct some kind of a set function that's defined on the space of hypotheses. And for every such hypothesis, you can plug that thing into this function. It will spit out some number, and that number represents the degree of belief in or the support for that particular hypothesis. So here I'm labeling this thing as an inferential model. And what this does is it takes the data we observe, it takes the model we assumed, maybe some other kind of things. It returns some kind of a function here, b sub y. And this function takes subsets of the parameter space to number 0, 1. Right? So then the idea is that this by with an a plugged in, a is like some kind of hypothesis. So this represents degree of belief or support in that hypothesis based on data, model, other things. Right? So this type of framework actually covers lots of things. So familiar, maybe the most familiar one is Bayesian using some kind of a posterior distribution. This would start with a statistical model, use the likelihood function combined with some prior to get a posterior distribution. Fiducial and confidence distributions, these are maybe less familiar, but roughly what these things try to do is to take, without using the Bayesian updating, so take something about the statistical model, maybe some kind of summaries of the data, and then convert that thing into a distribution defined on parameter space. But so both of these things here, I guess, one thing that's in common between them is that both are actually probability distributions, so things, the additive type of measures. But there could be other things, and in fact, what I want to focus on mainly here after I give some setup is some kind of an inferential model that's non-additive. So it doesn't have these kind of features of probability distribution, but I want to set that up to explain kind of why I think that's that type of extension is important. Okay, so back earlier I was talking about this kind of focus on some notion of reliability. And so I would make a claim here is that if there would be no point in constructing that inferential model if it's not valid in some, or reliable in some kind of sense. And so this actually turns out to be not so trivial. So there's I've sort of written it here as a quote, but I've kind of substituted in some slightly different words. The reason is that there's a specific context in which Brad Efron was speaking, but I've just translated that context into the one I'm focusing on here. And so he made this claim that, so this construction of reliable prior free inferential models is a most important unresolved problem. And so been working on this kind of thing for a while now. And so I want to share with you today, basically, how do I think we can potentially resolve this kind of problem. And so one thing that's, I think, has been missing, for the most part in the context of statistical inference is any kind of thinking about imprecise probabilities or this specific kind of thing, some kind of a non-additive type of beliefs. And so I think this is actually an important step to resolving this problem. And so this is sort of mainly what I want to focus on. And so there's, I guess, three kind of messages that I wanted to communicate here is that one is that these things, these additive beliefs, these probabilities, they're afflicted with something that's kind of not such a great property. And so we'll call this thing false confidence. I'll define that more specifically a little bit later. So first sort of message is that, well, there's some potential problems with using additive probabilities, but you can avoid those potential problems if you switch to some kind of a good non-additive belief. And of course, I'll specify what these things are. And then more than that is that there's actually a way to do this construction. So I'll tell you about these three different things. That's sort of my main objectives. So just as a quick kind of outline, so the first thing is to kind of point out what's that potential problem with additivity, and I'll frame that in a particular example. So this is something I see that Michael and Scott are both here. So this was some joint work that we did not too long ago where we looked at this kind of satellite collision example, and there within that context we formulated this result which we're calling the false confidence theorem. And so then once we identify, okay, there's a potential issues with focusing on precise or additive type of probabilities, then the natural thing is, well, what could we do to overcome that? And so going imprecise or non-additive is that next step. And I'll describe sort of how do we avoid that false confidence and how do we actually do this kind of construction. I'll show you a few examples here. They're not going to be super detailed just because of time and there's some technical things that are there, but try to show you, give you some idea about what this looks like. Then I'll come back to that satellite problem and sort of show you what's the difference between working with the additive probability like up here versus something non-additive after I just described that kind of construction. And I have a few other things just to sort of wrap things up. But so one thing, so you can see here at the bottom, says there's 40 slides. So there's actually not really 40 slides, but I added a handful of things at the end that have some kind of details. The idea, I think Simon mentioned it to me in email, that we'll do some kind of a presentation here, an hour, maybe definitely no more than that. And then there'll be some time where we could have some discussion. I thought, well, I'll have some things sort of prepared in case there's some specific questions, or if you want me to explain some kind of detail. So that's the plan. Okay, so jump into this satellite example. So what I wanted to talk about here is, okay, just to kind of set this guy up. So certainly we understand, okay, the satellites are orbiting the Earth, and I guess until I talked with Michael and Scott about this, I guess I hadn't really thought about it, but of course there's lots of things out there in space orbiting the Earth. Some things are, other satellites, some kind of garbage, various kinds of things. I know Michael can certainly say a lot more about this than me, so if there were questions about some specific details of the satellite collision problem, I'll probably pass those off to him. But I think we can all understand that, okay, if there's these other things out there, there's a chance that these satellites could collide with them. And that would be a bad thing, because of course it takes a lot of time and effort and money to get the satellites up there and operational. So if something goes wrong, then they have to fix it or launch new satellites. So it's actually a serious issue for these engineers to make sure that they can keep the satellites safe. Okay. So what they do is sort of on some regular basis, maybe semi-continuously, they're collecting data on position velocities and of the satellites, and using some kind of physical and statistical models about the orbits. And so what they do then is they would calculate this thing called the collision probability. Okay? And the idea is just that, well, if this collision probability is small, then these conjunction analysts would say, all right, I think the satellite is safe, and they'll do nothing. Otherwise, if this collision probability is not so low, then they do something. So this could, for example, to try to divert the satellite off of its current course to avoid some collision, these kind of things. Okay. So one thing that's was interesting, Michael pointed this out to me, was that there's this notion that's called the probability dilution. And so this is a sort of an unusual phenomenon that I think there was no sort of clear or sort of fully satisfactory explanation of this in the satellite conjunction analysis literature. But just to kind of summarize this one, somehow just having data that's noisier makes the non-collision probability large. Okay? So why is this a problem? Well, if you're judging the safety of the satellite based on that collision probability, if it just turns out that having noisy or messy or just not very good data leads you to think that the non-collision probability is large, you're thinking that the satellite is safe, when what's really happening is that you just don't have sufficient information in the data to tell you what's going on. So this puts these conjunction analysts at risk, and so that's I think is a serious problem. This has been discussed a lot in that literature. Okay, so just to give you some kind of an idea about what's going on, so this is obviously oversimplified, but just to give you some idea. So here, I have some kind of measurement that describes to me where the satellite is positioned relative to some other object. And so here I'm just going to think of this y as a vector, and I'm going to measure like the length of this vector, and the length of this vector describes kind of how far away the satellite is from this other object. And just to keep things simple, I'm saying that if this distance is less than or equal to 1, then that suggests that there would be some kind of a collision. Okay, so so this y is measuring y is a measurement of the distance, but it's not precise, right? So somehow there's noise in this, and so I can't say for sure whether there's going to be collision or not. I can measure this thing, but this measure could be small or large, even if the satellite is on a direct collision course. Right, and so the magnitude of these potential errors is controlled by some kind of a measurement error variance. So this is just call it here a sigma squared. Okay, so what I want to do here is I want to label this thing. I guess I'll have some different notation for stuff later. I don't know, I missed this. So this is the probability of non-collision given y as a function of the measurement standard error. Right? So what that probability dilution issue that I mentioned on the previous slide, what's going on here is that as the sigma gets big, this non-collision probability gets large no matter what the data is. Right? So here's a few examples of this. I know that maybe the axes are kind of small, but this is what's on the horizontal axis is the log of that standard error, and on the vertical axis is the non-collision probability. Okay, so in this case, that distance is relatively small, right, which suggests that less than equal to 1 is sort of suggested collision. So there should be some, we would expect that the non-collision probability should be relatively small in this case. Okay, and of course, that's what happens. If I have very precise measurements, small standard error, then this probability is small. But as that standard error gets larger, this probability just gets larger. Right? It's not that somehow we feel more confident or more confident in a non-collision. It's just that there's noise in the data. Okay? So this is a case where actually it suggests that the satellites would collide. So data seems to be consistent with the collision, but because of the large error variance, this probability could be large. Right? And you see here a few different cases where different values of that measured distance actually doesn't really matter. If there's sufficiently large sigma, then no matter what the data says, seems that the non-collision probability would be large. So analysts would just make a judgment that the satellite is safe when actually it may not be. Right. So what's going on here? So this is maybe somehow a different. There's maybe various different stories. So what I wanted to say here is just that I think what is clear is somehow the data is not sufficiently informative, and based on that sigma value, right? So it's not informative enough in all cases to sort of answer questions about collision, non-collision in a reliable way. So what we had thought about when we were working on this project was that, so it could be actually that, so this non-collision probability is of course an additive measure. It's based on the distribution of this, so a Bayesian posterior distribution for the sort of actual distance between the satellite and this object. We can make a noisy measurement of that. But anyways, at the end, this is a additive probability that's defined on this space. And so what we were thinking is that, okay, so maybe the additivity of that probability distribution is kind of forcing the probability to go somewhere, right? So it's not allowed to kind of same here. So so even if the data seems to suggest that collision is quite possible, somehow the non-collision probability can end up being large. Okay? And so this is a problem again because they're going to make a judgment about the safety of the satellite based on the magnitude of that non-collision probability. So we formulated a more general type of notion here that's a potential explanation of what's going on in this problem, and that's just this notion of false confidence. And it says that if there's a hypothesis tending to be assigned a large probability, even though the data doesn't offer some support for that. So that's what's happening in this satellite collision example, is that the data may not provide strong support for a non-collision, but the non-collision probability still ends up being high. Okay. So this actually turns out to be a fairly general phenomenon, and so here's a relatively simple result that would tries to communicate that in a more formal way. Is that just says that so take any kind of an additive belief, could be any kind of a probability distribution that depends on the observable data. So this could be a Bayesian posterior, could be a confidence distribution, could be a fiducial distribution, could be all sorts of things. So we don't have to say anything about posterior distribution. So take anything like that, and it says that so you can identify two indices here, an alpha and a t, any choices that you want. Then there exists some hypothesis such that here this means that the hypothesis is false, and here this means that it assigns a relatively large probability to that false hypothesis with it's not necessarily a rare event to assign this relatively large probability to that false hypothesis. Okay, so the easiest way to understand this is just in the words that's at the bottom, is that there always exists these false hypotheses that tend to be assigned high posterior probability. Okay. So this is bad again because I'm going to make judgments about the truthfulness of this hypothesis. And so if it can happen that this hypothesis is true based on posterior probability when it's not, then there's some chance that I'll be making some kind of systematic errors. Okay. So the theorem here is I guess in some sense this only suggests a potential risk because it doesn't really say how serious these hypotheses that are afflicted with false confidence. It doesn't say how serious it is or which ones happen to be the ones that are afflicted. It just says existence. So it's I guess something I'm interested in pursuing now is actually thinking about trying to give some kind of characterization to what those bad hypotheses are. And I can maybe share some thoughts about this, but we're still not to a point where I can say anything specific about it. But one thing I do want to mention here, just kind of going back to the statement of the theorem, is that so this is not an issue about, oh, I had I used this Bayesian model with like a poorly chosen prior distribution. So this actually says it doesn't matter what kind of posterior distribution you have. Any kind of prior updated to a Bayesian posterior would lead to this kind of phenomenon. Of course, different prior would identify different hypotheses that are problematic, but the existence of such hypotheses is always there. Okay, so just to show you this in what's going on in that satellite example, again, a sort of relatively simple formulation of this, but what I want to show here is let's take that hypothesis to be non-collision, and let's measure this posterior probability for non-collision. Okay, but now let's think of this guy as a function of the observable data. So A is now fixed, Y is the thing that can vary, and so if Y is random, like comes from some distribution, then now this posterior probability is a random variable, and that random variable has a CDF. Right? So what I'm going to do here is show you the CDF for that random variable for a couple different values of the sigma. And so those are the pictures down here, different colors are the different sigma. And so what's the axes here are a little bit messed up too, but so what you're looking at here is the CDF of that random variable. And so the most extreme one is the green case, where it's a relatively large measurement error. And so the green case, if you see like what does this mean in terms of that random variable, if you see this CDF pushed way over to the right towards 1, what this is saying is that this random variable is almost always 0.9 or more. Right. Same deal happens with some smaller kind of error variance. Here it's roughly around 0.6 or more. Okay. One might say that if the posterior probability for non-collision is more than 0.5 or something in that ballpark, maybe that means that the satellite is safe. But this actually says that always the posterior probability for non-collision is bigger than 0.6 or more. Right, so this is the kind of the manifestation of this false confidence for this particular example. As you get more precision, right, this gets a little bit better, but somehow we don't have all that. We don't actually have any control over it. It is what it is. Definitely it gets better as we have more precision, but we don't have control over it. That's maybe the message here. But anyways, here we see that for relatively large measurement error, which Michael mentioned to me before, is that in fact, in these applications, large measurement error is the norm. That somehow it's hard to get quality measurements of these things, so they often have very large estimates of this error variance. And so something like this, where you might say, okay, well, a variance of 4 maybe is a really large value. Michael says to me that that's not actually so extreme, that this is maybe is representative of the real applications. Okay, so my claim here now is that, well, we've identified some potential risks related to this notion of false confidence. And so, yeah, my claim now is that what we would like to do is to avoid it. And so just here's a quote that I like from Nancy Reed and D.R. Cox paper, this is now maybe 5 years ago or something, talking about, okay, if somehow we have a procedure that will, that the procedure is meant to represent some kind of uncertain knowledge, the same way that these posterior probabilities are intended to do, if you were to use those things repeatedly, like in different analyses of satellite collision data, if this gives us systematically misleading conclusions, then that should be unacceptable, right? So in one line, what I'd say is just this notion of unreliability that you see in that previous example. This is bad, and we should try to do something to avoid it. Okay, so the message here is that, well, okay, that false confidence theorem says that every additive belief or every ordinary probability is afflicted with this kind of false confidence. So there's no hope in just changing from one probability distribution to another. Those things will always be there. So the natural thing that we have to do is just consider these non-additive things, imprecise probabilities. So what I wanted to mention here, this is just to give you some idea. I think that some audiences I've presented these kind of things to, and maybe they're not familiar with non-additive beliefs at all. In statistics, we don't generally encounter these things. So I know I've talked to many people, and I mentioned something about imprecise probabilities or non-additive measures, things like that, and they've never heard of such things. And so I wanted just to give some kind of a tidbit here. I think this audience has some more familiarity with imprecise probability, but one kind of sense in which a measure could be non-additive is that if you look at two hypotheses A and its complement, that we don't necessarily have that the sum of those two things is equal to 1. So a probability measure is guaranteed to give you this plus this is equal to 1, but a non-additive belief, non-additive measure doesn't have that kind of constraint. So there's in some sense more flexibility in a imprecise probability or a non-additive belief than in an ordinary probability. Okay, so we want to emphasize is that it's not just a matter of just switching it from additive to non-additive and then everything's resolved. So it's not so straightforward. We have to do some work. It's not just that any non-additive belief can avoid the false confidence. We have to work for it. Okay, so this means imposing some kind of conditions on our construction of that non-additive belief. Okay, so this is getting to that more precise statement of that notion I mentioned before about reliability. So this is now a formal definition of what I have in mind here. And so remember we started out, I see I have a typo, this M is supposed to be the P, the model. So this is starting with some inferential model, which remember takes data, a statistical model, and maybe some other things and returns a data-dependent degrees of belief defined on parameter space. So this is going to say that this guy is called valid. So this is a definition. If the event where, so here this A is a false hypothesis because the theta is not inside of there. So what we're asking here is, so look at this event is like the event that the belief assigned to a false hypothesis is relatively large. So the requirement here is that this event, which I would say is not a good event because A is a false hypothesis and this is being bigger than something. So I would want to have some control over these bad things happening. So I would require that this event has relatively small probability with respect to the distribution of the data. Okay? So what this does is it gives us some control over the magnitude of these beliefs that are assigned to false hypotheses. So this is sort of directly making a definition that will allow us to avoid this notion of false confidence. So there's, I guess, a couple of details here about the stuff on the right-hand side. So here, this is intended to hold for any alpha. So what we're trying to do is get some kind of strong kind of distributional or stochastic type of approximations to this belief as a function of data. So I want to require this one for all alpha. One thing you could ask is, so why does it look like 1 minus alpha here and alpha here? So this makes some connection to like a uniform distribution type of relationship. So the claim here is that I need to be able to measure, or the idea is that I need to be able to know what does large and small mean so that I can make judgments in a real application. So if I want to say, well, I'm going to say that the data supports a hypothesis based on the magnitude of this, then I need to know what it means for it to be big and what it means for it to be small. So this having some kind of a concrete, very specific type of ways this depends on alpha is what allows me to make these judgments. You could say, well, why not pick some different kind of function of alpha here? So maybe let's take this alpha here as a fixed thing, and then this one be some other function of alpha. That's definitely is true. This function should be monotone in alpha in a certain sense. So the claim here, or my reasoning here is just that This is to make things simple. If you wanted to try a different one, you could reformulate this, or you could just think of taking that monotone function and just moving it to this side. That effectively just changes the how we're defining that belief function. And so then we could always work with this 1 minus alpha by just adjusting this one by whatever kind of monotone transformation I wanted to make. So I like this one because it's simple and interpretable, but there may be some kind of extensions one could consider. But I like it just to say sort of specifically what does large and small mean. Well, I'll give sort of more formal statement about this, but actually if we're able to achieve this property, it's unclear whether we can, at least I haven't told you that yet. If we can achieve this property, then this actually leads to some nice kind of results, which says that if I define certain kind of procedures based on this non-additive belief, so I'll explain that more carefully, but this actually has some error rate control guarantees, so that in kind of for those interested in sort of frequentist type of ideas, well, these procedures with error rate controls is exactly what they care about. So there's one other thing I didn't mention yet, and I've made a separate slide about it, but I wanted to, before I jump to that, wanted to highlight it here, is that I've mentioned in this definition of validity here that this should hold for all hypotheses. Okay, so that means that I'm not really changing the by function itself. All I can do is vary the argument, and so it needs to satisfy this thing. I'm asking it to satisfy this thing for all A. Right, that is definitely is a strong condition. So you could say, well, why might I impose such a requirement? Right, it's definitely is strong to insist that this thing would hold for all hypotheses. So what I was thinking here is that, well, I mean, the point of formulating this problem in terms of this kind of inferential model that can quantify uncertainty about all hypotheses, the only reason that one would do that is so that we can quantify uncertainty about all hypotheses. If I don't have this notion of reliability for all hypotheses, it means that if, for example, if one of those hypotheses shows up, then I have to change everything. Right, so then it's almost as if we're thinking about this more in the, I guess, the kind of the classical kind of frequentist type of strategy, where for every problem you just decide, okay, this is the best thing to do here, and if I change the question or I change the problem in some way, then I just start over from scratch and build something new. The advantage of this inferential model and looking at posterior distributions and things like that is that it gives you one thing that you have at the end. You take the data, you update, you get this kind of belief, and then that thing you can use to answer any question. So this could be used for inference, prediction, all kinds of things. There's some advantage to having this all in kind of a one-stop shop, that the inferential model, the belief can answer any question. So if there's somehow there are certain questions that can't be answered with this, then the usefulness is maybe less convincing. Okay, so what can we do? So if one thing I can do is definitely what I've already suggested, is that we could just impose this requirement for all A. That's one thing. The other thing we could do is to just try to figure out which ones are the problematic ones, so we can tell users of this technology that they can't use it to answer that question, but all these other ones you can. So I think both are reasonable. I don't know how to answer this first one about figuring out which hypotheses are problematic. Working on that. The other option is just to force this to hold for all the hypotheses, and so that's what I'm working on here. And this is sort of directly connected to why we need to be in this non-additive type of framework. Okay, so again, when I've presented some of these things to some different audiences, they're not familiar with non-additive beliefs, so I have to give a little bit of setup. I kept it here just for the well, because I don't actually know exactly the background of this audience, but I think there's more familiarity for sure with imprecise probabilities and non-additive beliefs here than what people I've spoken to before. But let me tell you, okay, here is what I think is one of the most simple ways to construct these non-additive beliefs, and that's through the use of a random set. Okay, so here I've set this up in a kind of a more general, kind of generic way, since it's not specific to our statistical inference type of context. But the idea here is like this, is that I have a random set, there's a generic space here, there's this bold X, and then I'm calling it here the random set. This is a sort of script X. It has some distribution p subscript x. So this is a set that's defined on, of course you have to do some kind of reduction to sigma algebras or whatever, but this is defined on the power set of all subsets of the X space. Okay, so so suppose I have this thing, right? So then what kind of things might I do is let's take some fixed subset of the bold X space, okay? And then we say, well, how could this random set X be related to that fixed set A? Right, so I take a realization of that random set X and I try to compare to A. Right, what kind of things can happen? One is that the random set X realization could land completely inside of A. Another possibility is that it lands completely outside of A. This would be contained in A complement. And then there's this third option, which is that it actually has some kind of non-empty intersection with both A and A complement. And it's this third one that makes it different from ordinary probability and random variables, is that if you're talking about random variables, you give a fixed set and you say, take a realization of random variable, it's either in there or not, and those are the only options. But here, because X is a set, it has three possibilities: totally in A, totally out of A, or non-empty intersection with both. Okay, so it's this three options instead of two that gives us the non-additivity property of this containment functional. So this is like, take this A and then define this B of A as the probability that the random set is fully contained inside of that set A. And then this defines a thing called a containment functional or some kind of a non-additive belief. And so this thing, because of the three possibilities instead of two, has this non-additivity property automatically. It just says that there's three options. It could be in A, it could be an A complement, or this other thing. And so it's this other thing that makes up the difference between one and this left-hand side. Okay, so back to the main context. So we're thinking about this kind of statistical problem, how to construct some non-additive beliefs for the statistical inference problem. So what I want to do is I want to start with here the reformulating or re-expressing that statistical model. That's like the distribution of y for a given theta. Reformulate this in terms of what is more or less an algorithm for generating data from that distribution. So the idea here is that I have output here on the right-hand side, or sorry, left-hand side, and then on the right-hand side are inputs. So there's the parameter value, and then there's this kind of random seed. Okay. And so the thought here is that, well, I generate some random point according to a fixed distribution. So often the way we think about this is maybe my computer can do random number generation. So I just plug, I ask computer spit out some random number, then I take that random number, I plug it into some mapping that depends on the parameter of interest, and then that will return a y that has this distribution py theta. So all this is really doing is to think about the way you would generate data as kind of a formulation of that statistical model. Okay, so what this does is it kind of changes our perspective. Is that if I just write down this py given theta, and then I maybe write down a likelihood function or something, then it's like focuses entirely on this parameter, and I don't know anything about that parameter, at least potentially. What's advantageous about this type of formulation is that it actually switches the quantity of interest to this auxiliary variable, this u, and less so on the theta. Right? The reason is that this is just some intuition about why that's beneficial. If I happen to know what the u was, then I can effectively just solve for theta after I see y and I see u, and I'm done. There's nothing else to do. I have sort of all the information that I would need to be able to answer questions about theta based on y and u. Okay. So now that intuition doesn't lead to any sort of practical utility because, of course, we don't ever observe this seed. Right? That thing is not part of the data that I can observe. However, I do know something about this u. And the reason I know something about this u is because it's part of this formulation that I set forth. Right? So this realization u comes from a distribution that I know. So maybe it will help to take advantage of that knowledge about this u to learn something about theta. Okay, so that's the sort of the intuition. So what I want to do here is I want to use that known distribution of u to construct what I'll say, here's a quote here, a guess about that unobserved value of u, right? The one that actually corresponds to the data I see and the parameter I don't know. Okay. So I'm using this known distribution of u to construct some kind of a guess. And so what's important here is that because I know that distribution, I have some control over the reliability of that guess. It's sort of completely separate from the data and the parameter. This is all just focused on the u space. Right? This is a known distribution. There's a quantity that I don't get to see, but I wish I did. Let's use some information about that known distribution to construct something which is good at guessing realizations from that distribution. Okay. Now, if I were to just use a random variable guess of u, of the realization of u, right? I could just take another sample, let's say u tilde, from this PU distribution and think of u tilde as my guess of where the unobserved u is. Right. That's actually a reasonable strategy, but kind of notion of reliability, because that u tilde will always be different from the u the unobserved u. So this is something to do with like a continuous random variables can't ever sort of agree. So what I want to do here is I want to take this notion of guess, and the way I want to formulate this is by kind of imagine like stretching out a single point drawn from this PU distribution into like a net. So think of this kind of set as like a net, which will now be able to capture that unobserved value of u with some probability. Okay, so I just stretch this idea of like a random variable draw from this PU distribution, just replace it by a random set, right? This random set of S to say it's the distribution of piece of S, but there would be some connection between distribution of S and this distribution of U, right? So, but I know the distribution of U, so I can construct this in really any way I want until I find something that I like, right? And it turns out that there's some theory that will help us guide this choice of the distribution for that random set. I'll say a little bit about that here below, but let me tell you how this part worked. So I have that this thing from before. So this expression here, which describes how is y related to parameter and this unobservable auxiliary variable. So I didn't mention, sorry. So this thing a, this a function actually is a fixed thing that I know, a normal distribution, right? I could say this would be take the mean and I add it to the standard deviation times the inverse CDF of u, or the inverse standard normal CDF with the u plugged in. So this would be one example of that A. So A stands for association. So I may at times refer to this as an association. This is just what associates the data y with the parameter u and this auxiliary variable, parameter theta and auxiliary variable u. Okay, so now how do we put this all together? So what I can do here is I have this random set now S. I have now what I'm going to do is I'm going to collect all of those parameter values which are consistent with the data I have, this, of course, this association mapping, and some u that's in the realization of the random set. So this is basically looking at like find all those parameter values which would be reasonable explanations of the y that we observe for u values that are inside the realization of this random set. Okay. So all this is really done is it took this random set on the u space and then just pushed it from the u space into the theta space. All right, so that's all that's happening here is that there's this relationship between these three quantities. I have a set for the u's, this set for the u's into a set of thetas, and this is the operation. Okay, so now this guy is now a new random set, and it lives on the parameter space. So the original S here lived on that space where the auxiliary variable lives. Now I push this into the parameter space. It's a new random set. It has a distribution. That thing depends on the observable y, but I can do exactly the same thing I did when I described that kind of generic random set type of calculations, is that let's just define that containment function, or here I'll call it the belief function. Just take that new random set here. This is kind of this push forward one into the parameter space. and you give me some hypothesis about that parameter, I can evaluate this containment functional exactly like before. Right, so this is just the distribution of this random set as determined by the distribution of S. Right, this is a new random set, like a function of this S here. And now I have a new random set in parameter space. I just calculate this containment functional. And that's the thing I'm calling here the belief function. Right? And by this construction, of course, we know that this has to be non-additive. So I've at least achieved in terms of constructing something that's non-additive, a non-additive belief on the parameter space. Okay, so that when something is non-additive, it actually helps to think about kind of a pair of functions instead of just one of them. So the dual to this belief function is what's called plausibility. And so this is just one minus belief in the complementary hypothesis. But you can also formulate this directly in terms of the random set. Just says, look at the probability that the random set has a non-empty intersection with this with the hypothesis A. Okay. And the non-additivity here just means that the belief will be no more than the plausibility. And there is some intuition, I think, for this, because you can say, okay, the hypothesis could be plausible but not believable, but if it's believable, then it ought to be plausible. So you have this some intuition here for this. Okay, so the main thing here is, okay, there'd be no point, again, in doing that construction if we didn't get something out of it on the back end. And so here's the kind of the main result. It says that, just to kind of summarize this, is that if we do the construction the way that I just described, with some condition on that choice of that random set, then I can avoid false confidence. I can achieve that validity property that was defined earlier. Okay, and so how does this, not really saying any details about this, because I think it gets us a little bit off track in terms of doing this in the first place, but this suitable choice of random set is not actually that hard to arrange. I wrote here basically what it is that it just says that I need some kind of a notion of some kind of summary of the distribution of that random set, and I need to require that that summary has a distribution that's, I guess, stochastically no smaller than a uniform. So this kind of thing, since I know the distribution of U, I can arrange this in lots of different ways. There are questions about what are the best choices, and this one is kind of part of still some kind of open questions. But actually achieving this validity is not hard. There's lots of ways to achieve it. And so I mentioned earlier achieving that validity property. And so if we want to think about things like in terms of frequentist style type of procedures for inference, we can actually do that. And we have some guarantees that come directly from the validity property. It just says that if I do a test that rejects if plausibility is smaller than some alpha, then this has guaranteed size alpha. And similarly, if I wanted to construct a kind of calling this a plausibility region, this just looks at all of those parameter values for which the plausibility of that singleton is more than the threshold. Then this will be this is guaranteed to be so this all comes as consequence of achieving the validity property. And in fact, at least for this guy here, the hypothesis test, this would actually, I could do this for any A, because the validity property is satisfied for any A. So I have a commercial here. So I realize that maybe there's no beach these days, but so some details about the construction that I'm presenting here are presented in the book, so you can check that out. I have papers, of course, on my website, so you can check those out as well. Similar kind of content. Anyways, just a quick commercial. So as an example here, one of the simplest things you could think of is the binomial. And so the binomial case says, okay, I have the idea here, y is like n trials. So this theta here controls the probability of success. So the way we can do this kind of thing is we can set forth, can set the association actually looks like this. One of the reasons I wanted to show you this is that this example is that association I wrote before was kind of written as like an equation, like y is equal to a theta u. That actually isn't necessary. All it has to be is some kind of a description about how you can generate data from that statistical model. So here in a discrete case like this one, there's not like this equality type of relation, but you can still define a mapping like that. And so the mapping actually looks kind of like inequalities, but still achieves the goal. This it's a relatively simple kind of random set. The idea here is that, so the U here is a uniform on 0, 1. So all this random set is doing is taking, its realizations are symmetric intervals around a half with a random width. Okay, so this U tilde here is controlling the random width. So it's actually a relatively simple kind of thing, although it's, I think, staring at that expression, it's not so clear, but in words, it's easy to describe. It's just these are intervals in 0, 1 that are centered at a half with random width. And that random width is described just by a simple random variable. So in terms of calculating these belief and plausibility things, it all boils down to calculations about this U tilde. So relatively easy to do, although the expressions look kind of messy. Here, this is just that kind of last step of the construction where you push the set in the U space to a set in the theta space. Again, it looks messy, but it's relatively straightforward to do. You can just plug in that association mapping there, and then look at all those parameter values that agree with that association at a particular S, or realization of the S. So this is the kind of the details behind it. Maybe it's easier just to look at some kind of pictures. So what to believe? So one of the things that we can show is that plausibility contours. This is just the plausibility function at singleton hypotheses, and just draw this thing over a range of those singletons. So that's this guy here. So 0, 1 is the parameter space. And so you see that in this particular case, what I observed is Y successes out of 18 trials. So if I were to guess what do I think the success probability is, I would do 7 over 18, right? So this is around 0.4, right? So the peak here is around 0.4, which is what we would expect, is that the values that seem to be most plausible are the ones that should be consistent with the like what the data says, right? So the 7 over 18 would be in really many senses would be the most plausible value. And so this is actually a measure of the plausibility, and this is large there. There are some other values in the neighborhood that are equally large. This is a consequence of the discreteness of that distribution, that you can't really tell the difference between 0.4 and 0.399, for example. Okay. Other thing we can draw is like, these are kind of like CDFs, looking at belief and plausibility for one-sided type of hypotheses like this, and again, varying parameter value. So this gives us a sort of a CDF, but there's 2 of them. This is kind of like the lower CDF, and this one is the upper CDF corresponding to the belief and plausibility values. So just a kind of a picture of what we can get out of this. A slightly more complicated example. So in terms of my, a little bit longer than I was hoping. So so Simon, it's okay between 5 and 10 minutes more?
Yeah, that's
okay?
perfectly fine. We're quite flexible with the time, so go a bit longer if you want.
Okay, I hope 10 minutes would be the max. So, okay, so this is, I won't show too many details about this one, but this one is actually a particularly challenging problem, and I wanted to give some kind of an idea about how this, what kind of things we get out of this particular type of formulation. So it starts as a relatively simple case. I just have IID samples from a normal distribution, and here both the mean and the variance are unknown quantities, so the theta here consists of the pair mu and sigma. So in this case, what makes it hard is that I'm interested in something that's sort of an unusual quantity here. That's what's called the coefficient of variation. So this is ratio of sigma. The quantity, it has a name, so it's somehow something that people are interested in. It's not a typical thing you see in terms of trying to estimate such quantities, but still of interest to see what kind of information we can gather from from our posterior distribution or non-additive beliefs, whatever. The one thing that's sort of unusual about this problem, and when I first saw these things, I was really, really surprised by this. I think that it's not so well known. So I think this is actually closely related to the false confidence phenomenon. And I can maybe say something about that later if there's some interest. So what makes this one a challenging problem is that for this one and a class of problems that are sort of described in more detail in this 1987 Annals of Statistics paper, but they show some results there that say, okay, for this class of problems, if you were to specify confidence intervals which have almost surely finite length, then the coverage probability of those intervals is actually 0. So if I just call it a 95% interval, that doesn't mean it has 95% coverage probability. So this sort of confidence interval here, I should have put this in quotes, because if I just define something, but it turns out to have finite length almost surely, then it turns out that its coverage probability is 0. So this sort of identifies a very challenging class of problems that, so for example, is like if I produce a Bayesian posterior distribution and I read off like the quantiles of the marginal posterior for this, this ratio phi, those have to be bounded, right? It's a probability distribution, so that the quantiles always eventually, you always eventually achieve them. So it can't be an unbounded interval from a Bayesian solution. It has to be 0. So using a Bayesian type of approach to this to extract some kind of a confidence interval actually would not be successful. I think that was quite surprising when I saw that. So what we can do here is this sort of a different kind of strategy, which is through this kind of inferential model construction aiming for non-additivity. And so how this has to go is that in order for this to actually be a good solution, we can achieve validity, but to make it actually a more effective or efficient kind of solution, we need to do some marginalization to eliminate basically the parameters here are not really of interest. We only care about this one. So there's an opportunity to reduce dimension and increase efficiency. So this marginalization achieves that. I'm not showing you any real details here, but ultimately the association looks relatively simple. And in fact, I can use the same kind of random sets that I used in that binomial example here because I've reduced the dimension effectively. So once I've done this reduction, introduced the random set, I can do the construction exactly like before. And in fact, this is guaranteed to be valid. And so one of the things that can happen is that, well, if it's guaranteed to be valid, then I can extract those plausibility regions or plausibility intervals from my plausibility function, and this has to have the coverage probability guarantees, right? That was part of the sort of general consequence of validity. So we can sidestep this issue about confidence intervals having actually 0 coverage probability. That can't happen in this framework because validity is guaranteed. So that means that somehow the results look a little bit weird, and so I wanted to show you kind of how does this look. So these are again those plausibility contours, but now for the coefficient of variation. My axis label here is wrong. So this is one case where I generated the data from mu is equal to 1, and so when mu is equal to 1, it's in some sense sufficiently far away from a problematic case, and so this plausibility contour actually looks really nice. And so this horizontal line here would be like, where do I do the cut? And so interval 0.6 to about maybe 1.4 is would be my plausibility interval. So that's fine. But there's a more problematic case is that if the mu happens to be 0, or I mean, this is extreme, you could take it something just close to 0, and then see, well, what does the plausibility function look like? Of course, if mu is equal to 0, then my sample mean from this data wouldn't be 0. So I don't have this issue about actually directly dividing by 0. But you see what's kind of weird is that in this case, when I draw that plausibility contour, it doesn't have this kind of vanishing on the endpoints type of behavior. So over here, what you see is that it actually comes down, but it never goes below the threshold here. And in fact, over here, it goes down below it, but eventually creeps back up and will, if I extended the range, so it is possible in cases like this, depending on what the data look like, that you can return some plausibility intervals that are unbounded. Right? And so that's key to being able to achieve that kind of coverage probability that I mentioned. Okay, so this is just to give you some idea about some added flexibility that you get from non-additivity, is that this plausibility function doesn't have to have that property like a probability distribution where quantiles are always going to be bounded. And this actually turns out to be another example where there's some kind of false confidence here. And so I won't go into details, but what again you see is that the Bayesian solution to this problem has CDF, which is sort of way over pushed to the right, which means that the posterior probability assigned to this, in this case, a false hypothesis, actually turns out to be large almost no matter what the data says, while the thing that's valid is above the line achieves this kind of validity. So what's I think is the more interesting thing is to kind of see how does, I sort of use the satellite collision example as a kind of a motivation, so it makes sense to come back to this and just share some kind of thoughts about what happens that Bayesian posterior distribution with this non-additive type of belief. So what I'm showing you here are the same pictures from before. The black lines are the same as in the original display. These are the non-collision probabilities. But now what I've added is the belief in plausibility for non-collision. So there's two of those lines. So I put one in red and the other one is red dashed. So what you can see is that there's some kind of similarity between the curves. So like for example, is that in this plot over here, right, over in the left side where the sigma is relatively small, the belief and the plausibility basically the same as the non-collision probability. But as you increase the measurement error, now things kind of start to change. And so especially if you get into this, like, maybe around the log is equal to 0, so like sigma equals 1, you see that something very different has happened. Those two curves have split apart. Right? Ability of large actually, and so missing in additive case is to be able to distinguish using the word here, but being able to distinguish that between those things actually seems to be the right type of way, in my view, to describe the type of uncertainty that's showing up here because of the increased error variance. Okay. And similar things happen in all three cases, or all four cases. And so what I guess is the main message here is that when you have noisier data, the belief in non-collision goes down while the plausibility goes up. But in these cases, the probability of non-collision from the Bayesian solution always just goes up, right? But in terms of the belief in plausibility, that's now gone. Is that what you see is there's a huge gap when the measurement error is large, and that should communicate to the analyst that, okay, there's a huge degree of uncertainty, and I can't say that I'm sure at all about the safety of the satellite, and so maybe I need to do something to intervene. So one last thing about this example here is that, so if I repeat that same simulation, calculate the CDF for this random variable, the saw before was that, especially in the green case, the Bayesian non-collision probabilities all tend to be close to 1, which is that indication of false confidence that there's some potential risk for making some misjudgments. In this right-hand panel, that's the part that's new. This one shows the CDF for that non-additive thing. And so these guys are all above the diagonal line. That's what the validity property guarantees. And so this just says that even this is a false hypothesis. In this case, I generated data from a collision course. So then the non-collision is false, and it says that I can't have too frequently, I'm not too frequently going to assign high beliefs to the false hypothesis. Okay, so I think I'm these are kind of more detailed things. So I think I will skip this, but I can say something about it if there's some interest. I'll just jump here to the end and just say, okay, what the kind of the takeaways, remember, were like, okay, when you're working with additive probabilities, additive beliefs, there's some risk of false confidence. And so the only way to sort of strictly eliminate this risk is to use something non-additive. We have to break away from additivity. I didn't say this, I skipped over this part, but there's actually some close connections between familiar things from, I guess, classical statistics like p-values and confidence. And actually more recently, we found that there's, in context of prediction in particular with conformal prediction, Glenn Schaefer and of work about this. There's actually some close connections between non-additivity in the context I'm talking about here and in that case too. Lots of things I didn't tell you. I guess one in particular was about this dimension reduction stuff. So I hinted at this before, is that when there will be certain cases when you have an opportunity to reduce dimension, and reducing the dimension will give you some added efficiency. But I didn't tell you anything about that, but that actually turns out to be an important part of the process. And then I guess in terms of things that we don't really have an answer to, this is, I guess, of course, an incomplete list, but things about efficiency we know a little bit about, and optimality we know a little bit about, but I'm not satisfied with the kind of theoretical results that we have. So this question here is really about, what does the random set look like? So I know how to specify it to achieve validity, but if you say, okay, what does efficiency mean? What does optimality mean? How to that should look like in order to achieve those properties. So that's something that still is not fully satisfactory in my mind. I've talked here exclusively about cases where we don't have prior information. And so that may not be always realistic, but what I think is a pretty interesting case is where you know something, right? You have some information about the unknown quantity, but not enough to formulate a full prior distribution that could be incorporated in a Bayesian analysis. So one thing that I like about the imprecise probability framework is that something weaker than a prior distribution can be specified. And so it would be of interest to look at, okay, how do you take this kind of, I'll say, quote, prior distribution that's described in terms of a imprecise probability, and then combine that with an inferential model that achieves validity, and do so in a way that, like, in terms of efficiency because of the prior information that I incorporated. So that, I think, is I have something going with a student now. We're kind of looking at trying to do this in some non-trivial cases. Questions about how to describe uncertainty about the model itself. So here I was taking the model as given and interest in the parameters of that model, but often we don't even know what the model should be. And so can we somehow describe in a way that returns some kind of, has achieved some kind of validity property, uncertainty about the model itself. And something, I mean, in many cases, the computations are not so bad. But I think there are questions about how to handle this in sort of a more, let's say, more general way, or at least a way that's more easily accessible. You know, Bayesian has MCMC, and this is, I think, is a super powerful tool. There would be, of course, some kind of notions of MCMC that could be used here, but that, I guess, still seems to be, that's not something I really know what to do. So I guess certainly if there were some suggestions about thoughts about how to do this in kind of a more unified way, that would be really awesome. Okay, so I had one other commercial. It's not worth to spend any time on, but basically develop some kind of a new open access publication platform. And so that reference that I mentioned at the very beginning is available there. A thing I like about it, it's that it's a platform where readers can post comments and various kind of things. And so then authors can take those comments and try to address them and improve the work. So the old version was out maybe in 2018. We have a new one coming soon. So if you're interested in this kind of thing, please check it out. If you have questions about it, of course, be happy to say something. But that was, I guess, the end of the things that I had intended to say. for
Job, I guess, has this.
Yeah. For the super. So a few questions just to help me understand it a little bit better. So in slides 8, I'd guess through 11, you are almost kind of blaming additivity for the problems that we see. But then in 11, you see problem. So can you give some intuition behind why additivity is the problem here? Or maybe I've missed it, but just like a brief kind of summary.
So I think you said like slide 8 here, like
Yeah,
so
yeah.
why does it seem as if the additivity is the problem?
So specifically bullet 3, additivity forces the probability to go somewhere. So that's kind of what I'm not sure I understand.
Okay, so yeah, I think maybe it would be better to sort of, I guess just state these things in kind of a slightly different order. So I think what I want to do is I want to jump back to the picture from here, and hopefully this will kind of communicate what I was saying, is that so the additive probability, the black line. So what somehow, because there's only one line, as you sort of make the data more noisy, it somehow can't distinguish between the support for non-collision and lack of support for collision.
Okay, I see, because one is the complement of the other,
Yeah.
and you necessarily have to choose one.
It's not possible for the posterior probability, the additive thing, to actually achieve this kind of split and have some kind of a gap to distinguish between support for and, so this picture here, for example, says that there's actually very little support for non-collision when say the error variance is 1,
Mm-hmm.
right? But it's still plausible. Right. So what seems to be happening here is that the posterior probability is more following the plausibility, but that's only one kind of picture of what's going on.
Right.
Is that because you have lots of noise, you really don't have support for non-collision, but because there's noise, you can't rule out the possibility of non-collision. And so the posterior distribution doesn't have the flexibility to capture that kind of behavior. And so that's the reality. But I think there's a potential risk to this, is that thinking that, basically because the error of high support for non-collision based on this posterior probability, make some conclusions that are wrong. And so that's potentially dangerous. And I think here, by being able to look at summaries like this one, where you can see the line split, now it's very clear that if your error variance measure is relatively large, that you just don't have sufficient information to make a judgment about the safety of the satellite. It's not really supported by data, but it's also not impossible. And so this wide gap between here is actually an indication of how much uncertainty there really is. And therefore, an analyst that can see these kind of things, they can get the data, they know roughly what's they have estimates of the error variance. So they can plug into these formulas and would be able to see that, okay, my plausibility and belief, there's a huge gap between them. And so that's an indication that, okay, the satellite, maybe in terms of the posterior probability, for some reason, it sort of wants to be supporting the non-collision hypothesis. And so the thing that's happening here is that in an example, you get to see this Y, you get estimates of that error variance, you can do these calculations, and you would be able to see that there's a wide gap between the belief in non-collision and the plausibility of non-collision. And that would give you an indication that, okay, I don't have strong support for non-collision, so I better do something to protect the satellite.
So you cannot be definitive about what exactly is happening, but you have premises to do something about it, at least.
Yeah. So at the moment, I don't really know what's going on.
Right.
So Michael, Scott, and I, we recognize the risk. And so develop some kind of things to address the risk. But the actual explanation of why this is happening, I mean, I guess in any sort of general sense, I don't know. I mean, I think you can make some kind of at least some guesses about this particular example. But at the moment, we don't have a clear picture about why, why the additivity property can lead you astray.
Okay.
Well, do you mind if I jump in? Or is that you? All right, this is Michael. Do you mind if I jump in?
Sure, sure.
Yeah.
Okay, sure. So my understanding of it is basically like it makes sense, to have a really low assignment of belief to collision. When your data are noisy, and relative to the data, collision is like a really small set of it's a really small set of values that would actually lead you to collision. So it makes sense intuitively that you get a activity then forces the rest of that belief elsewhere. And I feel like at the beginning of the question, you were kind of hinting at the fact, or you were asking about the fact that just non-additive period isn't enough to get us away from that. And that's just the fact that some non-additive belief functions are close to additive. You know what I mean? You need to get severely non-additive before you can start to enforce the validity criterion.
Right.
And just point Ryan had mentioned earlier about the satellite stuff, which was that I had told him that a ratio of like uncertainty to collision radius on a ratio of 4 is typical. Actually, ratios greater than 10 are typical, and it's not that the estimates of these orbits are really bad. Like if you look at the orbit parameter estimate errors, they're like 0.001%. But the thing is, orbit parameters, like something made with Duraxis and whatnot, they're measured in tens of thousands of kilometers.
Right.
So you can have like a 0.001% error in that, and that's still translating to hundreds of meters when you're projecting out your orbit, 3 days to a week in
It's a
advance.
scale problem. It's a scale problem.
Exactly. So the precise way to phrase it is that it's a really high uncertainty relative to the event that you're trying to resolve.
Gotcha. Yeah.
That's all. Just wanted. Okay, sorry.
Thanks.
Thanks, guys.
So, Alex Wimbush.
Yeah, sorry, I was thinking about the question, and I think it's been. I'm not so certain of the question right now. I need to mull it over.
I'm that way most of the time. Matthias, do you have a question?
Yeah, I had a quick question. So, I mean, first of all, very nice presentation. Thank you for that. It was very instructive. One question I had, I think you kind of hinted at the fact that you may be still looking at this, but I was kind of wondering if you look at the validity property, and one of the first things I would want to know, because I use a lot of robust Bayesian analysis in my work with various people, is say that you impose this on the lower posterior probability of some standard, maybe even conjugate robust Bayesian analysis, just to keep it really simple. Do you know what sort of constraint that translates into on the set of prior distributions? Must your set of prior distribution satisfy a certain thing for your property to be valid? Or, I mean, can you even do it with the robust Bayesian analysis, or do you suspect that maybe even with robust Bayesian analysis you cannot? Maybe that's not even enough to. Maybe you need to go wider than that. That's kind of.
No, I understand the question. Unfortunately, I don't have an answer. So this specific formulation I hadn't actually thought of like as a kind of one direction to investigate this. So, I mean, the way I was sort of thinking about it more was, try to to look at like let me say this a different way, is that I hadn't thought about doing it this way, like with the So think about taking a class of prior distributions and robust Bayes and see whether this kind of property can be achieved by the corresponding lower posterior. So I haven't thought about that. I think that would actually be really cool. I mean, because this would give some kind of indication about kind of what you need, like what extra kind of uncertainty you might need in that class of priors.
Right.
If it works, then that would say, okay, what do you need to be able to achieve it? But even if it doesn't work, that's also something, because it kind of says, like you suggested, that to be able to say that just a class of prior distributions with the Bayesian update isn't enough to rule out this the potential risks.
Yeah, well, the reason why
I like that question.
Yeah, the reason why I'm a bit concerned, but I don't know if it becomes a problem or not, is that in a typical robust Bayesian analysis, if you have a lot of data, your posterior becomes very precise.
Yeah.
And so I kind of would be interested in to know whether you have to retain some imprecision in your inference for this property to hold, which is both a good and a bad result, I guess, right? So maybe you want to have a fairly precise inferential model if you have a lot of data, but maybe those two things are not compatible with each other, and that would be kind of that would open up a whole host of new questions, probably, like what do you do if you have a lot of data? Yeah.
Yeah, I mean, yeah. So I mean, I didn't talk about these kind of things, but like you definitely do get. I mean, if you have lots of data, then even these non-additive things will tend to kind of concentrate.
All right. Okay.
Become more tight, but it's still, I mean, if you satisfy this thing, it's not getting too tight. So this one guarantees that it won't get too tight.
Right. Right.
So I mean, it is possible even in, I mean, at least at a high level, it's possible in a robust Bayes case, even though you have this kind of tightening with more data. That doesn't mean that this validity property is impossible to achieve.
Okay. Okay. Yeah. Thanks.
Yeah. Yeah. Thanks.
Yeah, that answers my question. Thank you.
Yeah. Well.
So Adolphus.
Yeah, thank you so much. First of all, Professor, thank you so much for your like Peter before, I'm not expert in this field, so I apologize if my question might seem very naive. So I would like to ask, because in this presentation, we are mainly looking at cases whereby this model, where you actually assume that you have all the data set that's available to do all these inferential things that we discussed earlier.
Yeah.
So my question is, could this be extended to an online case whereby you don't have all data at one time, but rather the data comes in as sequenced time steps? And could this be extended to such like dynamic?
Okay. Okay, so this is that's a tough question. It's not naive. Definitely is a tough question. So I think this one, unfortunately, I also don't have a great answer, but I will say something. So I can't say for sure whether there's something here or not, but maybe give some suggestion. So this is, I guess, relatively recently we had looked at kind of doing these looking at these prediction problems where models for how the data are generated was not specified. So this is often, like in machine learning, that's the way you often like to do prediction, is to say, I just want to use the data I have to learn. And so maybe I don't want to make model assumptions that could end up being wrong. So I was interested in this kind of problem. And actually, I had heard of these conformal predictions, but then didn't really know much about it. And so I looked into this more, and I sort of realized that there's a pretty close connection between thinking about this with the random sets and the inferential models and what does this have to do with your question? Well, it's that I know that in the conformal context, there are ways to kind of modify the basic formulation so that it achieves this, that it can be used online and still achieves the kind of online version of that validity property. So this is in the context of prediction. I don't know exactly how that would, if your interest was in inference about parameters, that maybe would change things a bit. But I guess there is some hope that what you were asking about can be achieved, at least in a prediction type of context. And maybe the right thing to do then would be to look at, okay, what's the connection between these things and conformal prediction in the not online case, and then see what would it look like to make it online. How would that change some of the construction, some of the properties? And maybe from that, once that is understood, could back it up to the, basically, go in reverse back to the original inference problem and try to see, can we do the same kind of adjustments to the static data set that I presented here, and do something similar to what was required in the prediction case to make an online version of the inference problem. So just speculation, I guess, but some potential strategy to try and make it work.
Sure. Well, nonetheless, thank you so much, Professor. So it was a quite clear answer. I mean, at least there's a direction, rather.
It's funny to me because I guess I know about using the word brilliant for these things, but we tend to, at least in here in States, brilliant is usually reserved for something very, very good. I don't know. So I don't know if my response qualifies for brilliant, but
no, but at least there's a direction, like a suggestion as to how we can tackle this problem. So I think that's better than nothing.
Thanks.
It's a long way from brilliant to better than nothing, I guess, right?
So let's say brilliant.
Alex, your hand is back up.
Yeah. I guess just coming back to Matthias's problem, if you have an approach that you intend to use, and you have some means of determining the confidence that can be assigned to some whatever hypothesis you're generating, could you use PDF plots towards the end of the presentation? I can't remember which slide specifically. Further.
You know?
A little bit further. I think it was one of the very, very.
The thing.
Yeah, like this one. Go back.
This guy?
These. So, if you've got your approach that you're using to generate confidence intervals, and you can find like the maximum confidence that can be assigned to an interval that doesn't contain the true value. If you plot one of these, if you just like Monte Carlo sample and plot something like that to just check whether you would be good to go with the approach that you're deciding to use.
Yes. I guess. Okay. Yeah. I mean that's all I did here was the of approaches, and I generated data.
I suppose, like, is there any flaw you could see where that might, using that approach to sort of as a check on whether potentially introduce false confidence, is there any potential that that approach might mislead someone because of the limitations of just plotting a CDF like this?
So I say, I mean, there's not. I think that seems fine. I think the only kind of limitation is just that there's a lot of things that you'd have to try maybe to convince yourself that it's safe. So you might have a particular hypothesis and then you want to try, but there may be actual true parameter values for which this would be a false hypothesis. And so in this picture, I just have one case, like here are some parameter settings that would make this a false hypothesis, and then I generated data from that. But if you wanted to somehow to say, okay, I want to convince myself that I'm not at risk, then you would maybe need to try this for lots of different settings of parameter. And so then that's lots of these different CDFs. So
Yeah,
I mean, well, you can do it, right? I mean, you could try as many different settings as you like. There's also one sort of, I don't consider this a major issue, but depending on the method that you're investigating, actually generating this plot could be expensive. So,
yeah, if you have a lot of combinations of parameters that you're trying to sort of search across to show validity.
Actually, the red line here is a Bayesian posterior. So this actually turns out it's not a very nice posterior distribution. So actually, to generate this plot requires MCMC for every Monte Carlo sample of so obviously, I mean, some things like actually all of these are done based on Monte Carlo, but like some of them are easy and some of them are hard. So if the procedure that you're using is something maybe that you have to use some kind of MCMC to even evaluate those posterior probabilities, then you'd have to do the MCMC for every data set you generate and every setting of parameters. Obviously not every, but however many that you'd like to look at. So it could potentially be expensive to do this evaluation. Like I said, I don't think that that's a serious issue. I mean, if you care about this stuff, then you should be willing to invest.
Invest the time.
Involved in a real problem should be willing to invest some time to make sure that they give a good solution. But it's not a trivial thing necessarily to draw these pictures.
Okay, thank you very much.
I can't, Sivan Mitra, I can't tell if that's a hand up or it's blue claws. I guess.
Yep. Yeah, I mean, I was gonna ask a question, but I think he's answered it. I mean, I was just asking about the in terms of the computational time. So is it feasible if you're dealing with complex systems with a lot of parameters? Would you resort to this method, or would you choose something else?
Okay, so I mean, I guess it depends on lots of things. Okay, so let me. So I'll talk here about this thing. So if okay, so where, at least in my experience, often the challenge in carrying out the calculations is actually not dealing with this one. But like in this one example, I kind of hinted at this, is that there's a dimension reduction that's happening, and how that dimension reduction goes. This one was one where I didn't really say anything about it, but the dimension reduction part is relevant for trying to make answers to be efficient. So like basically what this means is that I would want the so if I was going to return some kind of like a plausibility region for unknown parameter, I would like this to be kind of as tight as possible while still maintaining the validity property, coverage probability properties. So that's what I mean by efficiency, or at least basically what I mean by efficiency. So in order to efficiency, you often have to reduce dimension as much as you can. So in this basic formulation here, I didn't talk about how do you do this kind of dimension reduction, but so by dimension reduction, actually what I mean, I should clarify this, it means reducing the dimension of the u variable. The theta may not have to be reduced. Maybe you care about all of the theta. So if it's a high dimensional problem with lots of parameters and you care about all of them, then you may not be able to reduce dimension of theta, but it's still possible that you can reduce dimension of u. And so that process should be carried out. There are cases where this is easy, and then there are cases where this is hard. And so in the cases where it's easy or are satisfied with just achieving validity, maybe with some sacrifice in efficiency, this computation may not be hard. And so let me, I guess, to say is that, I mean, something that I don't have a lot of experience like in like engineering type of applications, but my understanding is that there's often some advantage to having, I guess, the model itself may be complicated, but there's relatively simple kind of expressions for how this all gets put together. And so there's like the, you know, like not to say that Kalman filter or anything is like a good thing, but it's a complicated system, but a relatively simple type of model formulation. And so if that model formulation is relatively simple in the sense that it's wouldn't be so difficult to generate data from this kind of expression, then it may be that actually these computations that I'm describing would be relatively straightforward. When the model formulation is, in statistics at least, there are cases where we want to write things like with latent variables and these kind of things. And so in a case like that, there may be some difficulty because the proper way to formulate the model is not one that you would sort of easily accessible in terms of writing down some kind of an expression like this. And so in cases like that where this expression would be relatively complicated, this dimension reduction step could be hard. And that would be the main bottleneck for the computations, not simply just the use of random sets. So the random set part of this isn't what creates challenges with the computation. It's more about the dimension reduction kind of things. So I don't know that that's a great answer to the question, but I can say that definitely computation considerations are things that I've not spent too much time on. Most of the problems are ones where I can do them, and so I don't actually, since I'm not kind of I'm not involved in like engineering problems. So it may be that I don't even know what kind of examples you might have in mind. But definitely the computation part is an interesting question. I wanted to highlight that kind of at the end of like, what are things that are still left to do? In particular computation, because I think that making this to be something that can be, the sort of sidestep is that in the Bayesian context, it's familiar, but the computations there are hard. What kind of the Bayesian advantage is that they know how to do them. Doesn't make them easy. But 20 years ago, they didn't know how to do them. And so somehow that got figured out. And so I think that there's an opportunity here to kind of think of, there's different computations, new kind of things that need to be done here with kind of using the imprecise probability type of framework. And so likely, I mean, it's at least possible that there are people in the imprecise probability kind of community who know how to do these things already, and I'm just not familiar with it. But I definitely think that computation is a challenge, and it's important. And if you guys have any suggestions about things you think would be useful here, I'd be first delighted to hear about that. But it's not something I've spent too much time on myself.
Yeah. Well, do you think that you can run these simulations in parallel? Because if you can do that, then you can easily just parallelize your simulations and save a lot of time. So do you think that's possible?
There are certain aspects can be, certain things can be parallelized. So like I guess, I'm not sure if this is what you were thinking about, but like in this case where I mentioned that it can be expensive to compute this thing. So what you could do is that, I mean, this just requires, it's expensive to compute this lots of times, but if you were able to parallelize, that computation can be done in parallel. These are just Monte Carlo simulations from independent things from the same distribution. So this thing could easily be parallelized. How to do parallel computing to like directly evaluate like these objects, right? So this is a thing that I would like to be able to evaluate without having to do lots of hand calculations. Not because I'm lazy, that's part of it, but also because I want to make this kind of more automated so that it's easier to implement. Of course, there's a very interesting question would be like, okay, this is just a probability with respect to the distribution of a random set. So could I somehow think about actually simulating the random sets in using Monte Carlo things and just do Monte Carlo approximations with this, where I just have kind of some kind of software package that just says, here's the random set I want, here's what the association looks like, generate these sets in some efficient way, plug them in, and just do these calculations exactly the same way that Bayesians would do. And these things actually, since you could generate these S's, these are coming from some fixed distribution. It's not like a Bayesian posterior distribution where you may not be able to simulate directly from that distribution because it's complicated. So you need MCMC, which means there's some dependence, and that's why it's hard to do parallel computing. If here you could just directly simulate these S's in some efficient way and do this calculation directly, this would easily be parallelizable. Whether that's a possibility, I don't know. But definitely there'd be no reason you couldn't parallelize some kind of Monte Carlo calculation of this quantity.
Okay. Thank you.
Do you mind if I jump in and say a thing real quick to advertise next week's presentation?
Yeah, go ahead.
Next week's presentation is going to be about a sampling-based approach to some of this stuff. So, or at least to start on that, in case that interests you.
Okay.
Yeah, because it's actually kind of, especially if you know what your seed variable distribution is and you want to make a consonant random set out of that, it's actually pretty straightforward to sample it and then make those samples carry their little pointwise plausibility values and then do math with that.
Okay, yeah, that sounds cool.
Are there any other questions? I don't see. If you have a question, don't hesitate to shout. I have a couple of questions. First, I should say that Brendan McCabe says that he met you someplace, and he's sorry he can't attend today because he's in Thailand, which I think means it's 1,000,000 o'clock there. So yeah.
I think that's the first place I met him was in Thailand.
Oh, really?
He's always there. I don't know. I guess I didn't think of that, but
he sends his regards. I've often complained. Am I wrong, or am I being hyperbolic when I say that you're hiding your light under a bushel a little bit when you just complain about these additive measures? I mean, it's easy for people not to understand how profound your claims are, because what you're really talking about is everything Bayesian, essentially. All the statistical inference methods that you've ever learned are wrong. That's what you're really saying, isn't it? Am I being hyperbolic?
Well, it depends on, okay, so wrong is, I guess, there's various ways you can think of it. So I think maybe Michael would have more of an extreme view about this, and rightfully so. But I guess for me, I would say that there's one way in which you could justify that claim, is that it's wrong in the sense that existence of any sort of this false confidence phenomenon makes something wrong. If that's the definition of wrong, then yes, that would be the claim. What I would say, I mean, there's maybe a bit more to it than this, is that this just, I mean, it throws some light on an issue. Like there's something that was maybe not fully understood before, and now there's new questions that we can try to answer. So in some sense, if we knew exactly what were the problematic hypotheses, and we could say, okay, this is a posterior distribution, Bayesian posterior distribution that is designed to do X, Y, Z, but not A, right? So maybe A is a bad one, but X, Y, Z, these are fine. So then we could just say, this is what it's useful for. There's a risk if you use it for other things. The problem I have is that, so what's a kind of a main selling point, in my opinion, of Bayesian type of framework is that you do one calculation, you answer everything. So all you do is you get this posterior distribution. I can simulate from a posterior distribution, say, and then any quantity of interest that I might be interested in, that's a function of of those parameters. I could get a posterior distribution for those and calculate probabilities and do them all. Right. So this capability to do this calculation is like I said, this is the selling point of Bayesian framework, is that you can do anything. Once you have posterior distribution, you can do anything. But like that, there's now there's kind of a flip side to this, which is, sure, you can do everything, but some of those things that you might do are going to be misleading.
Yeah.
So if we, whether it's to say, okay, scrap Bayesian because there's a potential for this misleading type of behavior, that's one option. The other option would be, can we try to understand better what's causing this misleading behavior, and B, how can we characterize the cases in which something's going wrong, and then be able to, in my opinion, that's also interesting. It's just to understand where those problems are, and leave it to, then at least people understand what's at risk. So they say, okay, if I'm not interested in that hypothesis at all, and that's the one that's problematic, then it's fine to do the Bayesian thing.
Right. So I sort of, well, I invited Simon Maskell, who actually works in satellite conjunction here in the UK. The UK is going to do their own satellite conjunction analysis. And I showed him your paper about your and Michael's paper about the collisions, and he said, his response was, well, I think we would have done it differently. And to be sure, I think, one thing you could do is not talk about the probability of non-collision, but talk about the probability of collision. There it's maybe a little clearer when you create the problem. But I sort of explain it as a joke, almost, when I say that, the one thing that frequentists and Bayesians agreed on was that you have to think about the problem, that statisticians and engineers have to think about the problem. And of course, being a caveman engineer, we don't know how to think about the problems. And it seems to me that if you have a potentially misleading method, then if you can't think well about the problem, you're in potential trouble, right? So that...
Yeah, I mean, so this is, I think, is especially relevant in this kind of context, and this is getting into some sociological sort of things, but like my job basically, just a kind of a description about, what my job is and what my colleagues do is like develop methods that can be used by others. So
right.
Like a common thing for people to do, like I've done it, people next door to me do it, they develop some method, they write some codes, they create like a software package, and then now that's available online. Anybody can download it and use it. So if they think, okay, this is a reasonable strategy for this problem, I'll download the software, crank out the solution, done. So so what that means though is that if this is a Bayesian solution, for example, then that person can generate samples from this posterior distribution and do anything they want. And there's no warning at all about something could go wrong. So it's kind of getting to the point that you have, is that if it's just grab some software off the shelf, get some output, and then think that you can do anything you want with it, this is the real danger. So if at least on the box, on the box where that software is in, it says, okay, you can use it for this, but not for this, then at least we've done our job to say, hey, look, if you choose to use it for this thing where it's potentially misleading, then that's on you, not on us. So right now there's this sort of message, I think, there are statisticians who understand this, but I think that there's kind of this message is that once I develop a reasonable Bayesian method, then just do it, and you can do anything you want with it. And I think that's the part that maybe that's a dangerous message when what you're trying to do is to kind of sell these tools to people in engineering or in medicine or these kind of things where they're not necessarily familiar with all the intricacies of the statistical problem.
Right. It's chainsaws. It's selling chainsaws to toddlers. But
yeah.
So I do have an actual question. A couple questions actually. You mentioned well, you were working on the prior less problems, and obviously using prior information in the form of weak priors is very exciting. But is there any place for the regular style Bayesian precise priors, or would that be a misunderstanding of what a prior ought to be, do you think?
Well, one thing is that if you have a precise prior distribution, then this has an effect on the posterior.
Yeah.
And so then if what you're interested in is this, something like a validity property, And in particular, the strong form that I was advocating for here, which is that that this holds for every hypothesis. So if the prior is having some kind of an effect, it means that there's going to be some hypothesis where the prior pushes it the wrong way and actually makes things worse. So somehow it's like the role that the prior would play here, it somehow needs to be done carefully, because what you would, at least my view of this is that what I would like to do is to not sacrifice on validity, but still incorporate prior information. And so it seems to me, I don't actually know the answer to this, but it seems to me that if it is a ordinary kind of proper prior distribution, then this is going to ruin validity, at least in the strong sense that I've described here. That because the prior is going to be somewhere, it's going to concentrate somewhere, and then other hypotheses, you know, so it could be that, okay, where it concentrates, that's going to force the posterior probability to back up. So where the prior distribution is more concentrated, hypotheses around there will get a bump from that prior distribution. So that will make them likely to be larger. And so if it happens that those things are false, then I'm actually making this false confidence thing potentially worse in that case. So I would need this prior distribution, whatever that would be. I think it probably needs to be something different than a proper prior distribution, like in the ordinary sense.
So the one topic that wasn't on your list of things to do in the future was account for stopping rules. And I think that's a really exciting one, because you kind of have to know what the stopping rule was to make inferences. But in the imprecise case, we often have the situation where we don't actually know what the stopping rule is. And in that context, it seems reasonable that our breadth should just simply be bigger to account for all, I guess, all possible stopping. Is such a thing conceivable and possible? What are your thoughts on that?
I mean, I think that seems reasonable. I mean, you know, in some sense, you should be able to achieve these things just by weakening the belief somehow. How to do that specific, you know, the precise details of that are not clear to me at the moment, but that's it. Taking something that's not valid, whether it's in terms of stopping rules or something else, and then trying to figure out ways to stretch it. You know, basically, you know, you can sort of imagine it's like Mateus mentioned before about the robust phase, and you have prior distribution, you get a class of posterior distribution. So then that gives you basically this, you kind of think of it as a set of things. If you stretch that set out more, then maybe you can achieve validity then. And so I think that would be maybe one way to approach this, this question about the stopping rule. One thing I guess I can say, I know that Peter Grunwald has done some things recently about dealing with like the things that he does. It's a little bit different than imprecise probability, but I think there's some connections with this. He's not really working with Bayesian posteriors either. And so he has some notion of what he calls safety, which is in some sense, some high level sense, is kind of analogous to validity. And so he's interested in some things like what he called safe testing. And so part of that safe testing is dealing with stopping rules. And so he has some results about that. I don't know the details, certainly can't explain it, can't do it justice, but I at least know a place to look to see maybe hints about it.
So I guess a follow-up is, you know, if we knew, for instance, that the stopping rule was one of two forms, and we had answers worked out for both of those structures, and we got, you know, the plausibility curves for each. Is there can we combine plausibility curves, for instance? I don't know, a max or operator or something. Is there a way to work with plausibility curves for that, or maybe for different models? You know, we assumed either normality or, you know, log normality. I mean, we weren't sure which it was, but it was one of those two for sure. Could we work on the answers to combine them? Probably not, right?
I think in some sense you can do in a conservative kind of way, like you suggested, is that if I have two curves, one for each case, if I do somehow the most conservative thing, which would be to look at the maximum plausibility between the two curves. This kind of thing, like if both of them achieve validity and you just make things like more extreme, more conservative, then definitely validity property would be maintained. I think the thing that you about the model uncertainty. So this is, I think this is definitely is something. So in cases like where you have where the parameters mean the same thing, like you have same parameters with the same meaning across different models. Something like this where you have basically some kind of an inferential model for both models, and then you try to pool them together in some kind of a way that's at least conservative so you don't lose the validity. This kind of thing I think is possible. The challenge I think is that you may entertain different kind of models and those parameters in the models are different. And so you wouldn't necessarily be able to say like, I have a inferential model for theta in model 1 and inferential model for theta in model 2. Even though I use the same symbol theta, they're not the same thing. And so it's not even clear whether they can be like,
right. That would be cheating for sure. Yeah. You could certainly cheat.
Yeah, I mean, there would be some cases where the parameters are in common. So like things like, you know, if it was like a regression type of setup where you thought about, okay, I have some kind of regression coefficients that describe like the center of the distribution. Like x times beta would be the center of the distribution. But I might consider maybe that distribution is normal, maybe it's a Laplace, maybe it's something else. But like those betas inside of there mean the same thing across models. And so something like that, you may be able to do a quick kind of combination strategy that would preserve validity across the models. It would, of course, be conservative. You give up something, but that is at least a strategy.
Okay, thanks very much. If no one else has any questions, which I guess we don't, we should, I guess, thank our speaker, if emotively there he is. It usually precipitates one or two, but not everyone like at the keyboard, I think.
I assume that you're nodding loudly, you're just on mute. So.
That's right. The cheers are deafening, but muted. Thanks very much, Ryan. It was really a great talk. I was really interested.
Okay. Thanks for having me. And so, yeah, I meant to say this at the beginning, but yeah, it's disappointing. I was supposed to be there a couple of weeks for the.
Yeah. Well, I think we'll still do that.
Yeah, that'd be great to
I may not live to see it, but I'm hoping that we'll still be able to do that at some point. Thanks very much, everyone. Thanks for your patience getting started. I think we've kind of used up the 2 hours that we rested from Professor Martin's time, so we should let him go. Thanks a whole bunch.
Okay, yeah, thanks guys for coming and questions. It's very nice. Thanks.
All right, thank you, Ryan.
Thanks.
Take it easy, guys.